Good morning. Today we are going to talk about particulate matter monitoring, or PM monitoring, in session 3 of Quality Assurance Common Sense. And to start off with introductions, this is me. I work at the Tribal Air Monitoring Support Center, which is part of the Institute for Tribal Environmental Professionals, or ITEP, which is at Northern Arizona University. And also on the line and presenting with me, we have people from Seldovia Village. We have Tracy Merrill and Michael Opheim, and they are there with equipment, with their DustTraks devices in their van, ready to go out and place them for particulate matter monitoring. And we also have Chris Fish from the Alaska Native Tribal Health Consortium. And we are going to talk for about an hour today. So I want to first emphasize again, as with all of our courses, this is a strict zone of there is no such thing as a dumb question, because if there were, I would be asking a lot of them. Keep in mind that if you ask a question, you're probably doing somebody else on the line a favor, because chances are a lot of other people have similar questions. So we're just going to go ahead and get started and talk about what particulate matter is. We're going to go over the National Ambient Air Quality Standards, which are abbreviated NAAQS, or sometimes people really get fancy and say NAAQS. We're going to talk about federal reference methods, abbreviated FRM, and federal equivalent methods, abbreviated FEM, and just I'll mention their requirements. We don't have a lot of time to go into detail, but we're going to focus mostly on quality control for screening particulate matter methods. So using devices that are not federal reference or federal equivalent methods, devices such as Minivols or DustTraks devices, that are used to get an idea of what the particulate matter concentration is in the air. We're going to talk about the different types of PM. This is a picture of a wood stove that produces a lot of PM10, and we'll talk about that. We'll talk about general quality control for particulate matter, and then, as always, I'm going to sneak in some data management and say again, write it down, or else it didn't happen. You might as well just keep that in mind. If you can't prove that it happened with some piece of evidence, like a piece of paper, it might as well have not happened. That's the first rule of data management. Write down more than you think you will need, and legible scribbles are fine. Lots and lots of material admitted into court is handwritten. So first of all, what is particulate matter? So we're talking about two categories in general, and of course particulate matter exists in a whole range. You've got really big chunks in the air, but we're not worried about the particulate matter that can get stopped by the hair in your nose. So if there's anything to take home from this, it is that you should breathe through your nose, because the larger particulate matter will get filtered out by the nose hairs in our nose. But what doesn't get filtered out gets into our lungs, and that's what causes people having to go to the doctor because they've got asthma, they've got breathing problems. Sometimes it gets to my eyes start watering. So the two categories are called PM10, or particulate matter that is 10 microns, and we'll kind of go over that a little bit, and smaller. And so that includes this other category of PM2.5, which is particulate matter that's 4 times smaller than PM10. So PM10 includes PM2.5. PM2.5 is really small. So PM10 is produced by smoke, by dust, roads, and this, and I'm sorry it's cut off at the bottom. Thank you, Wanda from Norvik, for providing these images. This is a picture of probably quite a bit of PM10 just at the surface here being blown up. There, PM10 is oftentimes blown by the wind, and it's generated from crushing, grinding rocks and soil, just like happens when you drive over it with a heavy vehicle. The finer particles that are 4 times smaller are produced most of the time by combustion. So something burning like the engines in vehicles that we tote ourselves around on. And it can include a lot of nasty stuff like toxic compounds, heavy metals. It's produced from automobile and other vehicle exhaust. Incomplete burning, so brush fires and forest fires where it's not burned at a high temperature, can produce PM 2.5. And then, of course, some really nasty stuff in smelters. So this is just an overview of the difference between the two, and you can do monitoring screening measurements for both. A lot of times people start off with screening measurements for PM10 because that, of course, includes PM 2.5, and it's easier to measure PM10. So just looking at what these are, so this is a human hair, this is beach sand, and then you can see that PM10 is about the size, just like maybe 5 side by side could fit in a human hair. So you could maybe just like barely see it. But then 4 times smaller than that is PM 2.5. So you would have to place 20 PM 2.5 particles side by side to span the width of a human hair. And I don't think we can see that with our eyes. So that's what we're talking about. And of course, the whole reason why PM 2.5 is of interest is because the smaller the particle, the further deep into our lungs it can get. So, you know, we've all seen pictures of our lungs with all those little bronchioles, tubes. Well, the smaller particles can get in there, and then it takes a long time for our bodies to cough them out. So, how do you measure particulate matter? Well, basically, you pull air through a detector or filter. If you're using a device like a Minivol where you place a filter, what happens is you put the filter in the detector, you turn on the pump sucks air through the filter, so obviously any particulate matter that's in the air gets stuck on the filter, and then you package it up really carefully, making sure not to shake it and shake the stuff off of it, and then you ship it to a laboratory where they weigh it and they compare it to how much that very filter weighed when they sent it to you fresh. If you're using a detector like a DustTrak kind of monitor, basically they work but some variation of shining light through the pumped air, so the air is pumping through a chamber, and there is a light source and a light detector, and again this is a simplification, but most of them work something like this, and then how much light gets through is proportional to the particulate matter in the air. So, you know, if you're shining light through, and this is the same way smoke detectors work, so except they use beta particles instead of light. So basically the more particulate matter in the air, the less light will shine through. So they work basically from the point of view of pumping air through something where there's a detector, or it actually collects the particulate matter on a filter. All methods use air pumping, air moving through the device, so the flow rate is absolutely critical for particulate matter measurements. So FRM stands for Federal Reference Method, and FEM stands for Federal Equivalent Method. And companies are always trying to get their devices onto this list, and EPA updates this list every 6 months or so. And there are hundreds of devices, and you have to use them really, really specifically in order to make what EPA calls attainment or non-attainment decisions. So in order to say that your air above your land doesn't meet, remember the NAAQS, the NAAQS, the National Ambient Air Quality Standards, you have to monitor for a full 3 years with complete quality control, and then provide that data to EPA, and then a decision can be made about whether your air is lower than the standard or higher than the standard. And that would be non-attainment. Your air does not attain the standard. So most people start off with screening measurements. So just to get an idea of what the concentrations are. And this is a picture of a Minivol. You can see there's different configurations of Minivols. This one looks a little bit different than the ones that I'll show you later. This is an older model. And a Minivol basically works just by pumping air through a filter, and then the filter is sent to a laboratory. Now, if you want to make measurements to compare against the National Ambient Air Quality Standards, then you must use an FRM or an FEM. This is written up in law, 40 Code of Federal Regulations, I think it's Chapter 50.7. Has extensive QA requirements, but for PM10 it's not so hard. So a colleague of mine monitors for PM10 out at the White Mountain Apache tribe, which is about 4 hours east of me here in the White Mountains in Arizona, and he operates 2 continuous PM10, and I have a picture of him on the last slide. 2 PM10 monitors that are FEM, federal equivalent methods, and he reports that data to EPA, and he's almost got a full 3 years of data, and his air so far looks like it is in attainment. PM 2.5, because it's smaller, remember those particles, 4 of them will fit inside a PM10 particle in terms of just their size. PM10 is PM 2.5 is so small that it goes back and forth between being a solid and a gas. So the tricky thing about PM 2.5 is that temperature is very, very critical. So the reason that there's really strict quality control requirements for PM 2.5 is because the temperature is important, because if the filter gets hot, then some of those particles will turn back into gases, and of course then they won't be stuck on the filter anymore. So that's why PM 2.5 filters have to be shipped back and forth from the laboratory to you and then back to the laboratory in a cooler with blue ice. So QC requirements for PM 2.5 are a lot more strict than PM 10. This is a picture of actually a portable FEM device monitoring particulate matter on the Navajo Nation, and you can see they're just barely at the limit of 33 feet from that temporary building there. And this is a picture of a TOM and a MET station. So you may have purposes other than comparing against the National Ambient Air Quality Standards. I mean, not to say that when your data comes in, you're not going to say, well, are we greater than 150 micrograms per cubic meter, which is the limit for PM10? But you can't take that data from a Minivol, and say, all right, EPA, use this data and tell us whether we're in attainment or non-attainment. But you may want to start off with screening. So that's fine. If you have different goals, for example, screening, and we'll talk a little bit about that, you don't have to use an FRM or FEM. But if you want to compare against the National Ambient Air Quality Standards in a legal sort of way, then you can use either an FRM or an FEM. And the FRM methods are all filter-based, where you have to change a filter, and the FEM methods are continuous. So basically the two technologies are a TOM or a BAM, and these are two different types of continuous FEM monitors. But we're going to focus on screening type devices. So these are pictures of Minivols, and we at the Tribal Air Monitoring Support Center have, I think, about 12 Minivols, and you can see they come in different models. This is the older kind, and now they come in these nicer cases, and this shows it closed, and it could be set up like this, monitoring. They have batteries, and the batteries, of course, is the problem with anything. The batteries run out. the batteries run a pump, so you can see it really drains the batteries fast. But this is basically the inside here, and you can see you've got a flow meter right here, one of those bubble type flow meters. And again, it's really critical that the flow rate be the flow rate that you want it to be, and that you monitor that as frequently as possible with any particulate matter monitoring. This is a DustTrak, and you can see again here it's in a case, and this is a picture from Seldovia Village, and then this is a little blow up of how it looks in the case, actually from the DustTrak manual. And then this is the device taken out of its case and put into this camo box that they used in Seldovia Village. So they're also fairly small and lightweight. So how would you use these screening type particulate matter devices? Well, you're going to use them to estimate the particulate matter concentrations. You could use them to find out if one place has a higher concentration than another. So in the Seldovia Village project, they monitored, remember, at 2 miles, like along Jackaloff Road, mile 2, and then another DustTrak on mile 4. So the difference between the concentrations at those two locations is very interesting to them. And then also to find out how concentrations change during events. So time of year, traffic, during days when there's high traffic, events, during days when people are burning a lot of waste. That's a lot of times people use portable screening particulate matter devices around forest fires all the time, at the perimeters of forest fires, at the perimeters of dumps, and near high traffic areas, to get an idea, just like they're doing in Seldovia Village, of what the actual PM concentrations are in the air. And if your concentrations are high, the data that you get, it doesn't mean that it's useless. It is very good data. The data that the Seldovia Village project gathered has all the QC. It's very well documented. The data can be used to justify spending more money to buy an FRM or an FEM that then can be used for attainment decisions. So again, keep in mind your end goal for this. You may want, if you find high concentrations, you want to make sure that all your QC is all in good shape. You did it, it's documented, because at some point you might be like this guy, who's Gary Elfie, our IT person at ITEP, standing in front of a group of people saying, look at this data, and we need to ask EPA for more money so that we can purchase an FRM or an FEM. So again, going back to quality control. So quality control, the purpose of it is to estimate and limit your error. And remember, the error is the difference between your answer and the truth. And the truth being like the true concentration of particulate matter in the whole air over your land. Well, obviously, we're only just taking a little bit of sample, and we're sampling it through a filter. So right there, we know we're just taking a sample. We want this sample to be representative. Remember, we talked about that in the first webinar. So that's why you pick your location very, very well. But what are the components of error? Well, first of all, you've got instrument imprecision. And the greatest factor for imprecision for particulate matter measurements is the wiggle, or the slight variation in flow rate. So you know the flow rate cannot possibly be constant. You know there's going to be breaks in the voltage at some point. You know, just slight wiggles will cause wiggles in flow rate. It could cause drifts in flow rate too, where it slowly drifts slower and slower. And that's the critical thing for PM, is the flow rate. Instrument bias, slightly low or slightly high, a flow rate that's slightly low or slightly high could be caused by this drift since the last calibration, since the last time you said, okay, I'm going to make sure this is really running at 5 liters per minute. Now, if you're taking a filter and you're shipping it to a lab, the lab can make a huge contribution to error, right? So they have to weigh the filter. Well, the scale at the lab doesn't work perfectly right on every single time. So they have a contribution to the error also. And then, of course, transporting the filter, it can get shaken. Temperature changes can cause errors. Again, remember for PM 2.5, if the temperature gets high inside that cooler, it sits somewhere for a long time and all the blue ice just turns into gel and it gets hot in there. Some of the PM 2.5 on the filter may turn back into a gas, and then when the lab opens it up and weighs it, it's going to weigh less than if that filter had been shipped in a really cold cooler where all the particles stayed on the filter. So again, precision. Just looking at precision error, you can never totally eliminate precision error. And the definition of precision error is it's wiggle. It's sometimes up, it's sometimes down. It's often called the random component of error, as opposed to bias, which is the systematic component of error, where it's systematically high or systematically low. Precision is the random component. And it's estimated by measuring what you want to be the same thing over and over again to see the wiggle. So this is just a picture of a scale, and you know from reading any scale like this, you know, it could be 5 liters per minute, right? But sometimes it's going to be a little low and sometimes it's going to be a little high. Sometimes it's a question of how well can you read that little needle. You know, sometimes that's a contribution to error too, like if you're looking at it at a different angle. And that brings up procedures. That is why it's really important to try to do the same thing the same way every time, because you don't necessarily know that just because you're looking at it right on every time that that's actually minimizing your precision, and then somebody else comes and they hold it down like they're wearing bifocals or something and they hold it down. Well, then it looks different to them. They're going to say it's, you know, like when you're looking at your speedometer and to the passenger it looks like you're going 95 miles an hour, but the driver says, no, I'm only going 65, because you're looking at it from a different angle. Well, that's why precision is minimized by following procedures. Look at the thing at the same angle every time, and that will minimize precision if you've got such a device that has like this reading error type of thing. So there's 2 sources of precision error. There's what happens in the field, and this could also mean like you're just sampling this proportion of air, right? There's all this other air out here. We try to make our sample really representative of like the whole air around Road 2 by Jackaloff Road by carefully placing our sampler in the middle, and we hope it's representative of everywhere. And then there's the lab. You could be like this guy, like I am in a lab, constantly spilling everything. And so the lab has a contribution to precision error also. So just so that you guys know what happens in the lab, what they do is they take a filter, and they have standard filters that they weigh over and over again. And they have little tiny standard weights that they put on the scale. And over here you can see this is Robert Mosley, who works in the Tribal Air Monitoring Support Center. And you can see he's got a little area here that's caged off, and he's got the filters sitting in there, and he has standard filters and standard weights, and he weighs them, and they're supposed to agree. Every time he weighs the same weight over and over again, it has to agree within plus or minus something. And if it isn't, then he knows that all the filters he weighed in that batch are suspect, and he needs to figure out what the problem was, fix it, and then weigh them again. So let's talk about what you guys have to do. So to estimate the precision error of flow rate for a Minivol. So the way Minivols work is they're supposed to always sample at 5 liters per minute. So if you start sampling on day 1 and it's reading 5 liters per minute, that's great. You put the filter in, you let it go for 24 hours, you come back the next day, you take the filter out and you measure the flow rate again, and now it's 6 liters per minute. Well, you know the target flow rate is 5 liters per minute. So you know, wait a second, it has to be 5 liters per minute. So at this point, you recalibrate it and set it up for 5 liters per minute so you're ready for the next filter. But you log your results. So here's just a little table that shows the measured liters per minute the first time, the target liters per minute, and that's 5 all the time, the difference between the measured and the target, which is 0, the relative percent difference between the two, which is just the difference divided by the target, and that's 0, of course, if they're both 5. And then after sampling, it was 6 liters per minute. So now it's 6, what you measure, what the Minivol shows on its little bubble meter is 6 liters per minute. The target is 5. The difference is 1. 1 divided by 5 is 0.2. You can already estimate your precision error of the flow rate alone based on this. The average of these two is 0.1, which is 10%. So this is just an illustration of how the flow rate and little variations in the flow rate are really important. This project has just started, and that's fine. A precision of 10%, you're probably never going to get too much better than that. I mean, a lot of times 15, 20% imprecision would be good. So, just to remember, 0.05 is 5%, 0.10 is 10%. Some precision is unavoidable, but you minimize instrument imprecision by keeping the flow rate steady at whatever the target is. You minimize other imprecision by following the procedures the same way every time, and let's hope the lab does that also. And you minimize anything that could happen during transport by carefully handling your filters and doing the same thing the same way every time. So how do we know that the flow rate is 5 liters per minute? You know, that's what the Minivol says, right? Its little bubble meter says 5 liters per minute. But how do we know that thing just isn't stuck at 5 liters per minute? Or we turn it on, anything going through there shows 5 liters per minute. You know, it says 5 liters per minute. We change the flow rate and it goes up. But is it really 5? What if it's 10 and it's just sitting on the 5 line? Well, we know because it has to have some sort of external calibration. So devices are shipped to you calibrated if you buy them from the manufacturer, but then stuff happens over time. They have to be periodically recalibrated. In this case, the DustTrak was calibrated by Chris Fish at ANTHC, and what he used was something like this. This is a handheld external flow rate transfer standard, and sometimes they're abbreviated FTS, flow rate transfer standard. And what this is you stick this white thing over the inlet and it measures the flow rate itself. So your device will be showing the flow rate, and then you stick this on there and it'll be showing the flow rate too. And the goal is that these two say the exact same thing. Because your device could drift, and you could see that this is a transfer standard. You can see it's got a nice EPA sticker. We have some of these at the Tribal Air Monitoring Support Center that we loan out to tribes when theirs are sent back to the manufacturer for recalibration. Ideally, such a flow rate transfer standard is used during the project and again at the end. But at least once, it's important to get some double checking of the sampler's flow rate. So this again is called a flow rate transfer standard. A lot of times I call it a handheld, just to distinguish it from, because your device has a flow rate detector in it also, but this is an external one. It's like a double check. So the conclusions about precision. Well, first of all, why is flow rate so critical? Well, it's because the particle size that gets to the filter or the detector depends on the flow rate being exact. So the particle size, now how that works, for example, in the DustTrak, well, in a lot of devices, they have what's called an impactor plate. sometimes they have a cyclone. But what happens is air comes through, and then there's this impactor plate. The heavier stuff, like stuff that's bigger than PM10 in this case, hits, it continues on because it's heavy. So it can't make this turn. So the lighter devices, PM10 and smaller, go because they're just light and they go with the air. But the heavier stuff bangs onto this impactor plate and then it doesn't make it through to the detector. But obviously the flow is really, really important to make sure that that cutoff of size, the particles that get stuck on the plate and don't make it into the detector or onto the filter, that depends on the flow rate. So the particle size is affected by the flow rate. And the device is designed so if you've got a PM 2.5 inlet, it has to have the flow rate exactly right, what the manufacturers intended and designed it, so that only PM 2.5 makes it around the corner to your filter. And then the amount of particulate matter that gets to the filter or the detector is directly proportional to the flow rate. Proportional means that if the flow rate doubles, then the particulate matter collected is also doubled. So, if you think you're sampling at 5 liters per minute, but you're really sampling at 10 liters per minute, then you're going to get twice as much PM, not thinking about the particle size, but just twice as much PM on that filter than if you really were sampling at 5 liters per minute. So the flow rate is really, really, really critical. Okay, bias. Remember, bias is a consistent jump, either always high or always low. So that would be, in this case, we're talking about flow rate. Again, if the flow rate is always high, then there's always going to be a little bit more particulate matter on the filter. Bias could also happen as a result of a transport problem. So if you somehow just move your elbow in a certain way and you knock particulate matter off the filter, and if you always handle it like that, sliding it into its little baggie a certain way or something, would that cause a high bias or a low bias? Probably a low bias, right? Because you'd be knocking some of the particulate matter off of the filter. Or could a lab problem cause bias error? If they have dust on their scale and they don't tear their scale before they start, would that be cause a high bias or a low bias? Well, depending upon how they do their math, that could cause either high or low. They could get confused about whether they teared it with the dust on and then they clean it. So it could cause either a high or a low. But in general, it'll probably show that there's more particulate matter on the filter than there really is, just because they've already got dust on their scale. So these are potential sources of bias error. Again, it's a consistent jump, always high or always low, and you really want to minimize bias. So how do you do that? A consistent flow rate at the target flow rate, so that's whatever the instrument manual says is the target flow rate, is critical. Again, they work by separating particles of different sizes based on how they act at that target flow rate. Sometimes the inlet is called a separator. You carefully follow chain of custody packaging and shipping, and we have a folder on the website where you can click and see different examples of chain of custody documentation. You write everything down. Some change that you made could cause a problem, and you might not realize it at the time, but you can go back and look at your logbook to see what changed at that time. If, for example, you see all of a sudden a jump in your particulate matter results coming back from your lab, you could go back and look at your logbook and see around that time when that change happened, what changed. And the only source you have for that are the detailed notes that you keep in your logbook. So, chain of custody records. The chain of custody record shows where the filter was, who was responsible for it at all times, when and how it was shipped, who received it, when they received it, and what did the filter look like, the filter's condition when it was received at the office, And then again, when it was placed in the sampler, you would note filter looks good, or filter is wrinkled, or filter has a hole in it. This is a chain of custody record for criminal evidence. It's the same thing. Basically, I'm a big advocate of giant Ziploc bags. You can keep your chain of custody records, your SOPs, anything in giant Ziploc bags, and that way they won't get wet. It's the same. What we're talking about is legally admissible evidence, and so if you keep that in mind, that we're basically advocating the same sort of procedures that the police use when they collect evidence, then that gives you an idea of how important it is that you do everything according to procedure, that you write it down, and you complete the chain of custody records. So this is an example of a chain of custody form. There's something wrong with the form filled out the way it is, and I hope somebody can tell me what it is. This is a form that it describes filters that were sent to the Navajo Nation. I'll tell you that. And you can see there's lots of scribbles on here, and that's fine. They're all legible. But you could see we've got filter IDs, we've got the filter cassette number that the filter was snapped into, the date it was weighed. This is actually a field blank filter. This one was a trip blank filter, and we assume this one was a routine filter, although they didn't check that box. It talks about who is the custodian of this piece of evidence, this filter, how it was shipped, UPS, the date it was shipped. I'll just tell you that what is wrong with this chain of custody is something I did to it. I obscured the sent to organization and the tribal office person name there because I didn't want that on the internet. Who knows what happens, but other than that, this is a really good chain of custody record. So I highly recommend a free and short online course, and the great thing is that you can get a completion certificate, and I've taken this course and it's really quick and it's fun actually. They've got little animations. So if you're using a filter method, or if you're doing water sampling or anything where you've got samples and you have to ship them or transport them to a laboratory and you have to deal with chain of custody procedures, EPA has a free online course. If you go to this link, first you have to register, and then you go back in, and then you go to My Training, and under My Training you see all the online courses. So I highly recommend this course. Again, you can take it and get a completion certificate from it. Blanks. Okay, so what are blanks? So for people who are going to be using filters or any sort of device where you take it into the field, you expose it, and then it's analyzed at a laboratory, blanks are critical. Blanks are things that are just like your measurement method, but they don't make the measurement. You carry them with you wherever you go when you go out into the field, alongside with the actual device that does the measuring. And the idea of a blank is that it measures anything that affects the result other than what you're actually measuring. So it is actually measuring everything else that you kind of have to subtract off. And it'll identify if something wacky is happening. It'll happen to both the blank and the device that's doing the measuring, but you'll know that it happened not during the measurement period because that's what the blank is for. So some of these things that can happen to a filter or a device can make the result greater. So contamination is one thing that everybody can easily imagine, where if you've got a blank filter and you take it out and you carry it with you and it's in the cooler, and then you've got a blank filter and filters that you're going to put, say, in your Minivol, and you take, the blank filter just stays in the cooler, you kind of lift it up out of the plastic bag with the filter that you're going to put in the Minivol, and then you put it back in there, and then you go through the whole process, you label it as a blank, you send it to the lab. Well, what if there was already dust in your plastic bag and it got on both the filter that you put in the Minivol and your blank filter? Well, in that case, the blank shows a result, and that's contamination, and then you know I've got to subtract that off of my Minivol filter because that got on both of them, and that's the purpose of a blank. A blank can also show you that there's a reason that something happened that decreases the result. So how could what happens to a blank show us that our result is low? It could happen with filter. If you think about perhaps something getting wet and then it dries, so it's not clear that it was wet at some point. If you've got a filter that got wet and you've got both a blank and a filter that was put in the Minivol, there should be some change that occurs to the actual filter that they can detect at the lab that shows that the filter medium was damaged. That's one thing. One thing that is really obvious in radon testing, and I'm really familiar with charcoal canisters. These are charcoal canisters that you just open up in an environment. The radon in the air gets adsorbed onto the activated carbon in here. So it's important when you're making measurements with charcoal canisters to use a blank because of the moisture in the air. So if you've got moisture in the air and you've got a blank charcoal canister and you just open it up and then close it, and during that time a lot of water gets onto the activated carbon, that basically takes up all the room that the carbon has to adsorb radon or anything else, and you'll be able to see that in the blank. So sometimes blanks are important to show us that our results are too high. Sometimes they're important because they show us that our results are too low. Kind of a blank is if you're making real-time measurements. So this is the DustTrak device, and I think this is Chris Fish's hand. And this is an excerpt from the SOP that the Seldovia Village Project generously provided, and their SOP is a great one because it's short and it's got little pictures like this and little arrows saying do this. But this is basically taking a blank, putting it up to the DustTrak inlet, and then measuring what sort of particulate matter is coming through, and it should be 0, right? So this is a sort of a blank that's used for continuous instruments. Labs must use their own blanks. They use their own blanks. I think every 10th filter that they weigh is a blank. And then trip blanks are just for assessing whether anything got damaged or contaminated during shipping. So trip blanks just go with the cooler and then sit in the office and then get transported back in the cooler back to the lab just to see if anything happened during the shipping process. Field blanks, again, they go everywhere the field samples go. This is a picture of a PM2.5 filter. So use blanks as recommended for the method. So whatever the method suggests, if you're using screening measurements, if you're doing an FRM method, blanks are very critical and you have to be really strict about using them. So let's get back to screening measurements. So Minivols. This is just an example of the type of QC that you would do if you're monitoring using a Minivol. So you get to your site and you check what happened at the previous run. So you had set it to run for 24 hours. Are there any lights on? Battery check light, flow rate light. And this could be, expand this a little bit, add some pictures, and this is an SOP. You remove the filter holder, you pack the filter very carefully. You do a leak check. Well, how you do a leak check isn't very sophisticated, but it's effective. You put your palm over the inlet and you make sure that the flow rate drops to 0. If it doesn't, then you've got a leak somewhere. You reset your timer. If you've got a flow rate transfer standard, you check the flow rate. And if you don't have one, you just use what the Minivols says and make sure it's 5 liters per minute, and you put a new filter in. So quality control has to be put into your procedures just as part of what you're doing. All this stuff could take a while because you have to write it all down that you did this. Accuracy for EPA means total error. So to really estimate total error, that means that you ideally, and this is what EPA does with the FRM and FEM methods, they send out contractors who might be less friendly than these people, but they kind of look like these people in that they come out and they set up a portable sample. They've got their own FRM or FEM. These people are going to set up a DustTrak, but it would be the same sort of thing. They do it side by side, and then they compare the difference. They're supposed to be the right ones. They compare with you, and if you're off, then that's an estimate of your total error. Remember, total error, because you might be just high that day or a little low that day due to precision. The total error includes both precision and bias errors. Now, most of the time, we don't have the money to hire auditors to come and make measurements side by side with us, which is good because most of the time we're starting off with screening measurements. If you go to FRM or FEM and you want your data to be used for attainment decisions to compare against the National Ambient Air Quality Standards, then you will have to participate in an auditing program where somebody comes out and makes measurements side by side with yours. PM10, let's just kind of go over PM10 federal reference methods. There are 2 methods that are common, 2 methods in general, a lot of different instrument manufacturers, but they fall in 2 categories. And this is a picture. I really love high vols because they look like big R2D2s to me. It samples at a higher volume. EPA, if people are still monitoring for total suspended particulates, that's how this method got started. And you use a PM10 inlet that directs only PM10 to the filter. EPA has a really nice handbook, 2.11, and that's available as well as another handbook for low vol sampling at 16.7 liters per minute. These are available at this website here. So for PM10, there's 2 categories of methods. Just looking at quality control that we need for high vol instruments, see where it says CFR, this is Code of Federal Regulations, and these are the sections. So I read this and made this table, and you have to do a flow for PM10, and some of you will probably be doing PM10 high vol sampling at some point, have to do a flow rate verification, which is a QC check, to make sure that the flow rate is exactly 1,130 liters per minute, at least once every quarter, and the flow rate has to be within 7% of your standard, your flow rate transfer standard, your handheld, and within 10% of the design value. And EPA calls the flow rate that it's supposed to run at the design value. So that's the device's design. It's designed to flow at this liters per minute. You have to do an actual audit where you have somebody else come in, or at least you borrow another piece of equipment. PM10, like I said before, the quality control isn't as strict as PM2.5. Every 6 months, and then you have to have side-by-side or co-located sampling at 15% of your network, which means that if you have 1, you have to have 2 side by side in order, and then 3 years of sampling if you want to have your data compared for PM10 against the National Ambient Air Quality Standards. So that's the QC for PM10. I just want to point out a few resources to you. I use this program. It's free. They ask you for money, but you can continue using it for years without giving them money, as I have. I think it's a German, one of these app people, and it converts everything. It's fantastic. It converts radiation units, all sorts of weird pressure units, that there are checklists. If you look at your device, most owner's manuals have checklists in the back, or at least something that you could just like turn into a checklist. I have a lot of Minivol documents, and I'm sure Chris Fish does also. If you're interested on Minivol, using Minivols, the batteries are a problem in colder temperatures, though, but they are good for screening type of devices. I also want to make a plug for my YouTube video playlist on bias and precision. I have 6 videos. It goes over more detail and a few simple calculations on bias and precision. Again, you know, people's like 331,000 people watch how to apply mascara videos, so it'd be nice if somebody was, I'm sure they'll never be as interested in bias and precision, but a few people. So there you have resources. Now let's talk about results. Okay, so we're just going to get a little technical now. So the lab results will come back with the net weight of the filter. So the net weight is the weight that it weighed after, so the dirty filter weight minus the tare weight, which is the raw filter weight. That's the net filter weight. That's what they're going to give you. So what do you do with that? You may get lab results in milligrams. You may get lab results in grams. Well, you want to get air concentration, right? We're trying to get to air concentration, and air concentration is micrograms per cubic meter, right? So we want something in micrograms. So if they give us results in grams or milligrams, we can convert that to micrograms. What do we still need to calculate concentration? If we get back from the result, the lab is grams, what do we still need? Well, we need the volume of air that passed through that filter, right? So how do we find out the volume of air? How many cubic meters? We know we want a result in micrograms per cubic meter. How do we know how many cubic meters of air were pushed through that filter? Well, we know that 1 cubic meter, 1 meter on a side, one large box, contains, surprisingly, 1,000 liters. Liters all squished up together in there. If you imagine little liter bottles all crammed into one big cubic meter box, you could see if they were really crammed in there, 1,000 would fit. And we know that our flow rate was just about 5 liters per minute. So what do we still need to calculate the number of liters, right? We know the flow rate was 5 liters per minute. How many liters passed through the filter? We need the number of minutes, right? So the timer on the Minivol says it ran for 1,440 minutes, which, this is a perfect run, meant it ran for exactly 24 hours, so 24 times 60 is 1,440 minutes. 1,440 minutes of pulling 5 liters per minute through the filter. So we've got it pulled at 5 liters per minute, and for this many minutes. Well, if you multiply the two, the per minute here cancels out the minutes here, and 1,440 times 5 is 7,200 liters. Phew. So now we have got the liters, but we know that there's 1,000 liters in 1 cubic meter. So if we say, okay, how many cubic meters? Well, we know we could fit 1,000 into 1, so this means we've got 7.2, right? So 7.2 cubic meters are pulled through a Minivol if it operates totally perfectly correctly for 24 hours at exactly 5 liters per minute. Now, if your device ran at 4.5 liters per minute or something, you would come up with something a little less than 7.2 cubic meters. And you should, and you better make sure, because if you divide by this many cubic meters, your result is going to be a little bit low. So again, concentration is the mass in a volume of air. So we've got the net filter weight now from the lab, and we converted it to micrograms divided by 7.2 cubic meters, and this gives us finally our result in micrograms per cubic meter. Now, so just for the sake of an example, if the lab comes back at 72 micrograms That's the net filter weight. And we know we divide by 7.2, that gives us 10. So then we know our concentration is 10 micrograms per cubic meter, if, for example, the lab came back at 72 micrograms. Just a few more little things. Micrograms is written with this Greek symbol mu, grams, and because it's a hassle to go to your fonts and change it just for this one thing, we use U, and that can be really confusing, instead of the mu. So if you see UG, what they mean is mu G, micrograms, and there's 1,000 liters in 1 cubic meter. Remember, there's 1,000 milligrams, which is abbreviated M, in 1 gram, 1,000 micrograms, UG or mu G, in 1 milligram. So that means in 1 gram, you've got 1,000 micrograms in every one of 1,000 milligrams. So 1,000 times 1,000 micrograms in 1 gram. And now we'll all feel like this guy and his horse. In other words, tired. So, going on to something a little bit more visually interesting anyway. What do you do with your results in terms of charting them? So it's important to provide some sort of chart with your data so that you can show people how results changed over time. And even though you can't use your data to compare against the National Ambient Air Quality Standards in a legal sense, you can still compare it against your screening-only measurement results. So, well, first of all, you're going to want to report the average concentration that you found over the time period that you monitored. Or you might want to calculate average concentrations by week, for example, or perhaps by month, or if you're doing a longer term study, average concentrations over a season. So looking at the average over the summer versus the average over the winter. But also really important are these charts, and this just shows 3 rows of data, and you could see that on June 1st for PM10, the result, and this is Minivol, let's just assume, Minivol data for PM10 was 95 micrograms per cubic meter. 6 days later, 145, almost at the standard of 150, which was reached 6 days after that on the 12th at 150. So the Minivol results were 150 micrograms per cubic meter. So in terms of charting this, you usually put the date along the x-axis. So you can see that the first value is on the 1st, and that's plotted, and Excel will do this for you, and I can go over charting in Excel next week. Excel will take this chart and turn it into, take this data table and turn it into a chart. And you can make your chart pretty with a few just little fixes. So this value here is 95, which is this value, and you can see it's 95 on the y-axis, and the units of the y-axis are micrograms per cubic meter. Then on the 6th, the value was 145 micrograms per cubic meter, and then on the 12th, the value was 150 micrograms per cubic meter. And what everybody always wants to know is, how do we compare with the standard, even though legally, in terms of an attainment decision, you can't do that. You can still compare against it. So I always put on my graphs a line that's red showing where the standard is, and that way, as you show your data, you can show what days you were over the standard. So here's the legend, and it shows PM10 with the values connected by the purple line, and then the solid red line is the National Ambient Air Quality Standard for PM10 at 150 micrograms per cubic meter. So what does this mean, though? In terms of making sense of it, you could see that your logbook records are incredibly vital, because this data here from last summer shows values fairly low for PM10, and again, here's this U for microgram per cubic meter. On the 1st, we went up to 55, not too windy. On the 4th, wow, it jumped to 225 micrograms per cubic meter. Then it went down a bit on the 9th, and then on the 15th, 325 micrograms per cubic meter, more than twice the standard on the 15th. And then it dropped back down again. So looking at that, you might wonder, is this, weird data? Look how it's jumping around. But you can go to your logbook, and the logbook entries were written into the comment field in this table, and you can see it makes total sense because on the 4th of July was fireworks, and that caused a lot of PM10 that was monitored. People were shooting out fireworks all night long. And then on the few subsequent sampling days, it started to get windier. It was very dry, and then this really high value was on a very dry day with wind, not terribly high wind, but it was very dry. And then it went way down again because it was raining. So that's why it's really important to keep logbook entries. So in conclusion, particulate matter monitoring all hangs on the flow rate and your documentation. And part of documentation is chain of custody for filter shipments and their proper handling. Keep all your values and notes. Never erase anything in your logbook or cross it out with more than one line, so that you want your original entry to be still visible. And common sense trumps everything. Look at your data as it comes in and make sure it makes sense with what you know is going on in your air. So this is a picture of Delbert Altaha from White Mountain Apache, and you can see he has 2 TOM units, and this is one of his TOMs. And he took the inlet off, and you can see in his hand is a flow rate transfer standard, an FTS, that he uses to measure the flow rate, and he compares the flow rate measured on his handheld device against what his TOM shows, and he may have to do calibrations if the flow rate is outside those limits. Remember, it was 7%, I think, he had to have within his flow rate transfer standard. And you can see that he's got a logbook and some field data sheets there. And he has 2 of these. He only has to go, because it's an automated, it's an FEM, a federal equivalent method. He only has to go once every 2 weeks to download the data and to do this flow rate check. I think he actually goes more often, but his 2 TOMs work great. So that is our conclusions of quality assurance common sense for particulate matter monitoring.